Hey folks, welcome back to my Unity project for EarthGames. Watch the first part of this series if you haven't already. Where I left off, I had created a globe of the Earth and made it spin on the y-axis. Now, I said the next step was going to be interactivity, but I lied. I wanted to do one more thing before I linked user behavior with virtual behavior, and that was rotate the Earth on any axis, not just the y-axis. To do this would require rotation with respect to the x-axis. Then any other axis would essentially be a combination of x and y-axis rotation. If you remember, the spherical coordinates I used to calculate the positions of each pixel in the globe take three arguments: radius, polar angle, and elevation angle. I used polar angle to rotate the globe around the y-axis, so it's natural to assume that the elevation angle could be used to rotate with respect to the x-axis. But few things turn out to be that simple. Instead of rotating with respect to the x-axis, incrementally changing the elevation angle rotates each pixel along the arc on which it was put by varying the polar angle. In addition, the elevation angle doesn't loop like the polar angle. The result is that the globe collapses to a single point at the North Pole. To illustrate what's going on here, let's visit exactly how one of these spherical coordinates is constructed. So, going into 3 space, we have the x-axis, z-axis, and the y-axis. So first, we pick a polar angle. So this goes from the x-axis being the 0th degree, and we might rotate like this, some angle theta. This gives us the base for our spherical coordinate vector. And so from this you can kind of see how when we increment this polar angle, it's going to rotate our sphere around the y-axis. It doesn't matter what the y value is. It could be a vector like this up here, and it would still rotate how one would expect. It would still rotate both of these vectors by the amount that we would expect when we're dealing with trying to rotate a sphere around the y-axis. Now, the elevation angle is a different story. So now that we've picked out this base vector, the elevation angle simply says how much to rotate it up from there. So this would be the elevation angle. So this is on the same plane as this base vector. So if you drew a plane containing both the y-axis and this base vector, you would obtain this square that I've drawn, but obviously it's a plane, so it extends out in all directions. And then you apply this angle to this base vector to change how far it goes up and down with respect to the y-axis. So this isn't really rotating with respect to the x-axis. It's actually rotating with respect to this new normal vector to the plane that I just described. It's rotating with respect to this one. And this is not the vector we want to rotate around. This is not going to help us when we're trying to rotate our sphere around the x-axis. So, elevation angle will not work. So, let's forget about the spherical coordinates for now. Let's instead focus on the mathematics. What are we trying to do? We are given a three-dimensional vector and we would like to rotate this around the x-axis. By the end of rotating this vector, we would like this vector to have the same x component as before. If we imagine this vector as representing one pixel in a whole circle of pixels, we would like this circle of pixels to rotate around the x-axis. So it's going to end up moving like this, but it's never going to change its x component. So let's just forget about the x component. Why not instead just consider the y and the z component? We have this two-dimensional vector right here, which is the combination of the y and the z components of our original vector. And we're just going to rotate this by a bit. We're just going to rotate it by a little bit. Retain the same length of this vector, so that these are the same length, and then put back the x component. So we end up with a slightly rotated vector, but it retained the same x coordinate. So it's still on the same path as before, but it retains the x component. So if we kept doing this over and over again, we would eventually come in a full circle, which is exactly the behavior we want. And this is exactly like the behavior of the polar angles. So this is essentially what I did. I have the z-axis and the y-axis, and I have some vector. I've just taken the z component of my vector and the y component. And so basically what I want to do is find this angle. So what I do is take the arctangent of y over z. And this gives me theta, where theta is this angle. Then I increment theta by a little bit, so now it's like this, theta prime. And then we want to construct a new vector, so I have the distance from before, let's call this dist, and I want to construct a new vector with this theta prime with the same distance. So basically what I say is that y prime equals distance times sine of theta prime, and z prime equals distance times cosine of theta prime. And these are my new y and z components. And if you remember, my X component is exactly the same as it was before. So now I have everything I need. I have a method of inputting a three-dimensional vector and the number of radians which I want to change the vector by with respect to the x-axis, and these are the equations that I would use to do that. I've noticed more and more the value of understanding mathematics, specifically geometry and physics, when it comes to coding games. This was also the result of careful planning. While I was away from the computer, I was working through the mathematics I just explained in my head. Then when I came to my computer, I knew exactly what to code. It took no less than 5 minutes to code, and it worked the first time. When you come up against a complex mathematical problem in your coding such as I often do, step away from the computer for a while. Just imagine the problem in your head. Think of ways to simplify the problem. The solution will come to you. Alright, back to Earth. It worked like a charm. Here's a combination of x-axis and y-axis rotation. I was thus far satisfied with the aesthetic of my globe, so it was time to start working on some functionality. My goal at this point was to allow the user to click and drag anywhere on the globe to spin it. It might have been easier to connect the rotation with some arrow key interaction or some arrow buttons on the screen. However, gamers these days demand quite a bit of convenience. So for something as integral to this game as looking around the game world, I wanted it to be as straightforward as possible. You swipe across the globe, and it spins in that direction. You click and drag on a pixel, and the globe follows your mouse, using that pixel as a pivot point. Just to start out simple, I made a predetermined point on the globe follow your mouse. To make it follow my mouse took a bit more mathematics, pretty much the reverse of the geometry I explained before. I'm given the vector of the pivot point and the vector of my mouse, and I have to determine the change in the angle that would cause the pivot point to move to my mouse. Unfortunately, the behavior got a little buggy when the mouse moved outside the sphere. This was an eventuality I had planned for in my calculations, and even then it was buggy. So I simply removed any behavior when the mouse left the sphere. From there, it was a simple matter to connect this behavior to the user interaction of clicking and dragging. Simpler than I thought. At first one might look to onMouseDrag, which is a base method like update that can be defined on any game object, is what I thought, until I realized that onMouseDrag is only applicable to game objects with colliders and GUI elements. Neither of these components were practical. Colliders because I was not using any physics, and GUI elements because they would not fit to the size of the pixel appropriately. So clicking anywhere on the screen would likely result in clicking on the same oversized GUI element. So I instead decided to jury-rig my own onMouseDrag. Essentially, every time the user clicked on the screen, the update method would pick this up, and decide whether the click was close enough to the globe or not. If it was, it picked the closest pixel to the cursor location to be the pivot point to rotate the globe from. Then when the user let go of the mouse button, the update method would remove this behavior of the globe following the mouse. You may have noticed by now that the globe carried its momentum for a bit after I let go of the mouse button. This was also simple to implement. Whenever the globe moved to the mouse, it would also record this movement in a velocity variable, which is used when the globe is not being dragged to keep the globe moving in a particular direction. So as soon as the mouse is let go, the last recorded velocity takes over and begins to move the globe accordingly. I also added a friction constant which would decrease the velocity over time. causing the globe to come to a smooth stop. That's the end of this video. I implemented complex rotation and added some functionality by connecting rotation with a mouse interaction. Next time, I plan to add more interactivity, with the prospect of narrowing the scope of the game from what is currently just a tech demo. So, until next time.